at that limit, right? So I can do things, make it safe. All right? That's a common sense, right? I control the stress below that. Okay. However, okay, let's say I design a bridge. I say I can put 10 cars on top of the bridge. It will be safe. I calculate this stress point, right? Now, is this bridge safe?
No.
Will you feel comfortable stand there?
No.
Okay, say you can put 10 cars. I found there are only 9 cars. I can walk there. You feel safe?
What kind of
Why?
cars?
It's not safe enough, right? Why is not enough? Because let's say somehow the wind blow over, or somehow the car just makes some weird jump. Someone put the music on, they just bumping up and down. Right? Then you will increase the load. Then what happens? The bridge will fail because you're going beyond this safe point, right? So now, how can we make it safe?
Well below that.
You want to well below it, right? So let's say this bridge can put 10 cars there. Okay, you only put 2 cars there. Then you can walk there very safely. You feel, okay, there are 10 car limit, so there are only 2 cars, then it should be fine. So basically, you want to well below this point, right? So for this curve, let me just draw this one here. Okay, so this is the sigma, and then this will be this linear part, and then let's go this way. So this is the sigma y. Okay, so you want it way below this point, right? So you want the stress either here or here. You never want the stress go up here, right? That's when you think about it. Now, when you actually do a design, engineering design, how can you implement that? How do you calculate? Basically, you say, oh, make it lower. But you need somehow, when you do the calculations, you need a number, right? So how can you do that? Basically, now people introduce this concept called safety factors. Okay, so what's a safety factor? Okay, it's this one. So I want the stress, right, will be equal to the limit, let's say the sigma y, and then divide by n times. That's the stress limit. So we call it allowable stress.
N times?
Yeah, so basically, this is the limit. I divided n times. So basically, 1/n of the load, 1/n of that limit is I allow the stress to go that much. Okay. Let's say the limit is 10 cars. So therefore, I put 2 cars there. I say, okay, I designed this bridge. There are only 2 cars allowed to pass this bridge at the same time. So basically, 10 limit, right? Now I allow 2. So what's the safety factor I have here? 5, right? So because 10 divided 5 times, that's 2. So basically, the safety factor will be 5.
So we determine N on our own.
Yeah, you determine. Actually, first you determine. Now, because engineering already developed so many years, right? So there are lots of standards there. So if you design this chair, okay, maybe they'll say, oh, you need a safety factor of 2 or 3. That'll be fine. Okay, but if you design a nuclear reactor, you don't want a safety factor of 2. Right? You want safety factor of 10, 20, right? Or water dam. So depending on the importance, you can make this safety factor really big. So there are engineering standards there. Actually, there are manuals there. You can check what's the standard requirement. So for different structures, we give them a different safety factor. Right? This way, face the need. Right? If there are buildings outside, there may be oftentimes wind or tide kind of coming up, then you want a bigger safety factor. For chairs here, if it fails, not a big deal, you buy a new one, right? Nobody going to die because it's just a chair. So therefore, you want a safe material, right? You don't want, spend a lot of material just build a chair. Right? So basically, safety factor versus the cost, actually sometimes it's a balance. Right? That's why you don't use high safety factor for everything. Because if you design a chair, a safety factor of 20, right, then you need to use lots of materials. And then you actually pay a lot. The chair will be very, very expensive. Right? So basically, it's a balance between cost and safety. Right? So engineer, right, therefore here is your call. Okay? how safe should it be and how much money you want to spend on it. So both save cost and maintain safety, it's the responsibility of all the engineers. So you need to keep a balance there. Right? So it's actually sometimes can be a tough issue. Right? Also, based on the requirement, it all can be different. Right? For example, you design something to prevent a flood in 100 years, or you prevent a flood maybe in 5-10 years. The requirement safety factor will be different, and so the cost will be different. So basically, whenever you want to make things really, really safe, you will use lots of materials, the cost will go up. So basically, these two things, you have to maintain a balance. Okay. So that's when you go to engineering practice, that will be a tough issue. Okay, for this class here, okay, basically, we just practice, know this equation, the relation, and do the homework problems. Okay, so therefore, next let's maybe use one example, kind of explain this concept, put it into a real situation. All right. Okay, so maybe I'll just use this one already, draw it here. I don't have to redraw it. Okay, so here is an example. Okay, so I have the two cables, right? Oftentimes you need to combine the two cables. So this joint here combine the two cables, right? So the two cables, then you have the force here, apply 100 Newton here. Just make it easier, come up with a number 100, right? Then this cable must put in the same, right? Is that correct?
That's correct.
Correct, because always equilibrium. Remember equilibrium. We never talk about dynamic movement. We talk about equilibrium. So you have an action, therefore this one must balance it, and so you have one here. Now, for this joint here, you have to put a bolt, kind of combine them together. Now, the question is, okay, for the bolt, all right? Okay, so for the bolt, let me use over here. Okay, so for the bolt, right, we can make it ask a question differently. For example, I know the load, right? Now I can ask you how big is the bolt I need to select, put it there. Let's say, remember the basic parameters are A, right? Cross-sectional area, length, and material. Remember we talked about that? Okay, let's say I know I have a steel material bar. I know the material, so I know E. E is known, right? And I need to put a bar there. So the question is, how big should I select this bar to put it as a bolt there?
Get your strain.
Okay. How to do the analysis? This is like a homework problem, right? Okay, now what's the approach?
Free body diagram.
Free body diagram. Figure out the load there, right? Then you find out the stress there, and then you check the stress. Make sure the stress is safe, right? Okay. Now, how can we do that? Free body diagram. Okay, for this structure, right? If we draw the bolt, let me draw the bolt here. So if I take the bolt out here, what's the forces applied on this bolt?
100 and 100.
You have this part is from this part.
That's 50.
Okay, so this range, let me draw it, maybe more, make a shade here. So this part is pulled by this one, so you're going to have a force pull here. And then this contact, this part, so there will be a force pulling here. And then this middle part is in contact with this part of the cable, so it's pulling here, right? This is kind of like the load applying on the bolt. Okay, now what's the value? What's this one?
100.
It's 100,
Newtons.
right? Now what's this one?
50.
Most likely 50,
Yeah,
50,
something
right?
like that.
Because the total must be 100, balance it. Right? Can be different, but you just make it easier, assume they're the same. Right? Okay, so now this is the free body diagram. Is it complete? Yes, right?
Yes,
Okay, so we know this one. Now, what's next? We know the load now. There's 50 here, and then 100 here.
Balance equation.
Okay, as a bolt standard, when you pull it, right? This one pull this way, the other end pull it the other way, right? So what kind of Subtraction in the body is and the shear, right? So you try to shear this way. So basically the bolt, if I want to figure out what's the force in the bolt, right? Remember we talked about you need to look inside, how it deforms depending on how the load is inside. Okay, so we need to look inside. Now look inside. How do you look inside? Make a cut, right? Okay, let's say I make a cut here. So if I make a cut here, okay, now I can draw two free body diagram. I can draw the top part or I can draw the bottom part, right? Make it easier, let's draw the top part. Okay, if I draw the top part, I will keep this one as black. So the top part will be, this is the one. Okay, I make a cut here, and now you have 50 applying here, right? Okay, this is the free body diagram, the top part. But is this one complete?
No.
No, you're going to have a reaction here, right? So I can use the red because that's from the cut here. So you have a reaction here. And this one definitely is a shear. Okay, so therefore I use letter V. Okay, now can we find out this V? Yes. Everyone can find out this V value, right? How? Equation of equilibrium, right? Equation of equilibrium. That means minus V plus 50, right? So basically it's sigma fx equals 0. Minus V plus 50 equals 0. So what's V? 50. Okay, now we know V. Okay, so we know V. Now, what's next? Can we find out stress?
Do we have an area?
Do we have the area? Yes, we know. Actually, no, we don't. We are designing. We're trying to find the area, right? Okay, so can we find the stress? No, we cannot yet. But that link the stress, that link to the area, right? So basically, the stress supposed to be this V. I know it's 50. Then divided by the area, right? Okay, so I already know V. I'm looking for A. Now, how can I find out A? I need to know the stress tau, right? So if the tau can go very high, then I can use very small area. If the tau can only go very low, then I have to use a bigger area. Okay, so how can we decide tau?
The modulus.
Material. Now we know this is steel, right? Okay, for steel material, I know this material. So I can go to the menu, find out this G, right? If I need it. Actually, in this case, I don't need it. But what else I can find from the menu, from the material handbook? I can find, I know this material is a steel, right? Okay, so for steel, I can find out it's a sigma y, right? Actually, that's right. So for steel, I can find out it's sigma y, and also find the tau y. So basically, for this material, I can check the menu, find out how high the stress can go for normal stress and for shear stress.
So you find your F max.
And in this case, I don't care about the sigma y because in our situation is tau. So basically, I found this one, tau y, from the menu. Okay, let's give a value. What's the tau y we find from the menu? Give, let's say 200 megabar. Okay, 200 megapascal. That's for steel material, something close to that range. Actually, sigma can go down, right? Okay, let's say we know that we found from the menu, because I know I use this steel. Okay, now what's next? Now, basically, I can say, okay, so I wanted the tau smaller than the tau y, right? That will be safe.
By how many times?
Or can be maybe go to this one, the limit. Let's give me the limit. Right? Okay, so from here, I know, basically I want V over A can be smaller or equal to this tau y equals to 200 megapascal. Now, can I find out the A?
A minimum area.
Yeah, so basically A will equal to, A will be smaller, or bigger, or equal to this limit. Will be V over tau y. Sorry. V over tau y. Right. Okay, so then I found out this A range. Okay. But now as I said, there is no safety factor. What's the safety factor we are designing? We design n equals 1, right? So there's no safety consideration there. Basically, we allow it to go up to the tau y. Okay, now, if this cable is important, so if we want the safety factor, let's say, give a factor 5.
Sure.
Okay, let's say we want safety factor of 5. Because this thing is important. We don't want it to fail. Okay, now, how this will change?
40 megapascal.
Basically, we want to find the minimum A, right? The size of A. Okay, once you want the safety factor 5, how high the shear stress can go? The tau allowable stress, right? How high you allow it to go?
40.
It will be equal to tau y over n, right? So that basically 200. That's for the material can go 200. But I want safety factor of 5. So therefore, this will be 40 megapascal. That's what I mean by safety factor. Okay, I want safety factor 5, right? This material allows stress go to 200. Therefore, I divide 5 portion. Okay, it's 40. So I allow the stress only go to 40. Right? Okay, so with this requirement, then I'm basically saying, okay, so the V over A, that's the tau, right? This is from here. Okay, from here. Okay, that supposed to be smaller or equal to the tau allowed.
1.25.
Okay, smaller sometimes it's hard to think. Let's say we consider the limit. Okay, what's the smallest A? Or what's the highest stress you can go? It basically is an equal sign, right? So you can use the equal sign, just calculate the limit. All right. Now, with this one, let's say basically this is 40. Now, can we find out the A?
Yeah, 50 over 40.
Can we find out the A?
Yes, you can.
Okay, A equals to what?
50 over 40.
Will be V over tau allowed. Right? So that basically is 50 over 40. Okay, what's the final answer? It's 1.25. Okay, what's the unit?
Millimeters.
Okay, now the calculate. So what's the unit for this one? We have 50 Newton, right? So this will be Newton. Now what's the 40? Megapascal. Okay, Newton over megapascal.
Meters squared.
It's basically, it's equal to, let me just write it here. So it's basically 50 Newton over
Meter squared.
40, this cancels out, over 40 M and then Pascal.
Meter squared.
Okay, we can throw the M away. So M, what's M? 10 minus 6, 10 6, right? Okay, let me write it here. So basically 5 over 4, and then times 10 6.
Millimeters.
Right? So therefore, when you calculate, this go up. So basically this times 10 minus 6. What's the unit? Meter.
Squared.
So basically,
Squared.
yes, squared. Thank you. Basically it says 1.25 square millimeter and 10 minus 6. Okay, so what does this mean? That means 1.25 square what? Millimeter. Right? So is this equal to 1.25 millimeter square? Okay, if you feel strange, okay, check the unit. Link this meter square to millimeter square. Okay, double check the relation there. All right?